Well, hi, everybody. Welcome. I think we're still waiting on a few people that are going to show up, but we start on time, right? So that looks like that's Brett. No, that's not you. Who just joined? Oh, Lauren.
Lauren.
Okay, thank you. So, just a couple of reminders as we get going. No class, of course, next Thursday. On December 4th will be our last official class meeting. Then's the final. So you can take the final anytime between uh well, you can take it now for all I care, up until about the second week in January when I'll do the certificate. So anytime, but sooner is always better. So the date of the final exam is the 11th, but of course you can take it whenever you want. The only difference in the final exam and the quizzes is that I give you one question at a time, and that's how the exam is offered, is one question at a time. You can go back and forth, and I'm pretty sure you can with the exam as well. So, but I thought I'd do that. And of course, it's a random selection of questions from throughout the class, so many of which you may have seen and many of which you may not, right? And if you take it over and over again, which you may, if you'd like, but if you take it over and over again, then you will get different questions. And again, don't spend any time memorizing the questions because these are my questions and they're unlikely to show up on the exam. So just a heads up on that. Culinary arts starts on January 15th, and I have already enrolled Trevor and Daniel Diaz, who you don't know, but he'll be there too. So if anybody's interested, if you've taken it last year and you want to take it again, of course you're willing to do that. Just fill out the registration form and then I'll know. Maybe send me an email. So the other thing is that in Southern California, the Research Chefs Association is not particularly active, but once a year we meet with the Southern California IFT, and the Southern California IFT section is very active, and they meet every month. So we always meet at Jenny Rossoff's Village Green Foods, if you know her. And so this year she's kind of seeking donations or support or anything if it's in your purview to do that as an RCA member, that might be nice. And you could reach out to her if you want to, or if you know of somebody. Usually what she does is she clears out her plant. She doesn't have a really big space, but she clears everything out, puts it all up to the side. And then we bring in a guest speaker and then food, so different kinds of food. So I don't know what the guest speaker is going to be yet, but usually it's pretty interesting and it's usually very, very well attended. So if you're in Southern California on February 18th, please register and come by because it's always a fun event. It's really fun. We always have a good turnout. So, anyway, so the learning objectives for today, there are a lot of them. I'm not going to cover them all. I think we covered most of them in the questions, but we'll start with food safety and sanitation. So commercial sterility is all about food safety. That's why we do it. So it's to kill off any pathogens or spores, pathogenic spores. So the first one is explain commercial sterility as it relates to pasteurization and be able to define process lethality, including DFZ and F sub zero values, listing target temperatures for lethality of Clostridium botulinum, and explain the importance of calculating these thermal death curves as it relates to consumer safety. Well, as far as I know, only the D value is explained in the culinology text. But because this learning objective includes all of them, I'm going to cover them all here, right? So to help you understand them. So here's a few definitions. Commercial sterility. So what we're doing when we're retorting is not sterilizing the food. For if we were to sterilize the food like a medical thing, then the food would be unedible because it would be way overcooked. So we call what we do commercial sterility, and that's the destruction of all pathogenic and spoilage organisms that can grow under normal storage conditions. And it includes both, let me see here, both vegetative means living, and spores. Lethality is how deadly we are, right? How deadly it is. Process lethality is defined in the temperature and the number of minutes of our process. And so that's what process lethality is. And then the target temperature for lethality of Clostridium botulinum is 250 degrees Fahrenheit, which is 15 pounds of pressure. So remember from last week when we talked, and we talked about we talked about low acid foods, right? So particularly we're interested in botulism in low acid foods. So can anybody give me an example of what's a low acid food?
Like tomato sauce.
Yes, it can be. It didn't used to be, but it is now.
That's a canned foods in general, Jill, I believe are considered low acid foods.
Which ones?
Like green beans, vegetables in general, right?
Right,
Green
vegetables.
vegetables in the can or corn, etc.
Yeah, vegetables, not fruit. So it's, oh God, I can't spell anything today. Oh, here we go. Vegetables.
That'll do.
I can, all right, vegetables. Okay, so vegetables, green beans and things like that, not fruit, because fruit has a high enough acid content. And I said tomato sauce, so it kind of depends. Tomatoes are kind of on the cusp. They used to be much more acidic than they are now. So they used to be able to can them in a boiling water bath. But today's tomato sauce, tomatoes are not. So unless you add some kind of an acid to it, it's going to have to be retorted process. So then the thermal death curve is a graphical representation of the resource process. So it's your retort process on a graph. So these are kind of some definitions of the words up here, right? What these words are. Um, Principles of commercial processing. I'll talk a little bit about milk pasteurization, but really retorting, it's all pasteurization. But the difference is we tend to think of pasteurization versus retorting as being a less severe, less heat, less severe process. And here, this one I wanted to draw out process products attributes. So remember last week when I showed you that chart, right? That had the square in it like this, and it was, I think there was water activity going up and pH going across, or the other way around. Anyway, a comparison of water activity and pH. So that's what it's talking about, product attributes. So ingredients, water activity, and pH. Ingredients could include also things like additives, like antioxidants and things like that. And then requirements for storage conditions. So remember that some of these needed to be refrigerated. So because they weren't complete. So you guys remember that I talked about that last week? Yeah. So that's what this statement is talking about. Does that make sense? To make a little clearer? Okay, we'll talk a little bit about heat transfer. And then I'm going to talk a lot about these DFZ, DZF, and F sub zero, the process. So just a quick, why do we cook? Right? We cook to stabilize the product and to ensure wholesomeness and safety and to extend shelf life. So what is heat? So heat is the vibration of the molecules. Let's just think about water molecules. So when water is cold, when it feels cold to us, the molecules are really close together and they're not moving very much. The atoms are very close together and they're not moving very much. The warmer it gets, the hotter it gets, the farther apart the atoms are, and the more vibration there is. And that vibration of rubbing up and down against each other is what we feel as heat when we touch it and it feels hot. So that's really what we're looking at. It's a vibration. So we can never add cold to something, but we can, we can equalize the thermal equilibrium so that so cold never transfers, but the heat transfers to the cold. And so you get this because obviously the heat is moving really fast and the cold is moving really slow. So when they come into contact with each other, you get something that's kind of in the middle. And if anybody talks to them about thermodynamics like that, they probably throw me out of the class, right? So, but that's all we need to know about that, right? So, but the one thing that we need to know, of course, is about the different methods. So, convection, we all know that because we have a convection oven, but also think about a pan of boiling water and how the water falls and it gets heated at the bottom and then it rises and the cool air goes down the middle. That is also convection like in water. And we have conduction. So these are the two that are the most important when we talk about retorting and process. Another thing to note is that if the temperature difference between your product and the temperature it is. So let's say we're talking about cook chill, right? So we put our product in a ice bath, right? And so the product is up here, usually it's about 180. The optimal fill temperature is about 180 degrees Fahrenheit. A lot of that, depending on the product, but that's about where it is for safety. That's what Jenny told me anyway. So it's here. Rapidly, you get rapid cooling at the beginning, and then the closer it gets to the temperature of the ice bath, the slower it's going to be. So in other words, you were talking about a two-step process, right? So in the first step, there's a big difference between the two, and then as you get in the second step, they're going to be closer together and you're going to get it cooling. Probably there's a difference in the water temperature too. Okay, this is Daniel. Hi, Daniel, welcome. So so just know that when you first start out, you think, oh man, this is going to cool off really fast. And it does, it cools off really fast. But the closer it gets to the temperature you want, the slower it's going to happen. So the first bit of cooling is going to go really rapidly, but the second is not, it's going to slow down. Any questions so far? Okay. Um, we're talking about it ask about wet bulb versus dry bulb measuring temperatures. So a wet bulb temperature is essentially if you have moisture around the end of the bulb, therefore a wet bulb, right? And it's the lowest temperature at which air can be cooled by evaporation. So that is the wet bulb temperature. A dry bulb temperature is just the temperature we measure in the air. So, but you might use a wet bulb if you have like a steam condition or something along those lines. That's where you'd run into that. And the difference between the two is humidity, how humid the air is. Any questions? All right. Well, good. I think I'm going to sneeze. Okay, logarithms. So I don't know you guys, but math was a long time ago, right? A long time ago. And logs were something that didn't really think I needed, right? A long time ago. So logarithms are a way of thinking about exponents. So an exponent is this number right here, this one up here, right? And essentially, an exponent tells you how many zeros it has or how many times the number is multiplied times itself. So 10 to the fourth, we can see that there are 4 zeros. And it means 10 times 10 times 10 times 10. 10 to the 12th means there's 12 zeros, 3, 6, 9, 12 zeros. And it means 10 times 10 times 10, 12 times, right? So that's what a log is. So far, so good? Yeah, got that? Okay, that's what a log is. So in order to plot something that has a really big curve, we use what we call semi-log paper. So essentially a semi-log paper. So this part down here is the standard 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 50, whatever, right? That's the standard. The log paper is done every 10 adds another 0. Every 10 adds another 0. So I'm at 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. I would count these. And then this is 10 times 10. So log to the 2 zeros. So now it's going to go 20, 30, 40, 50, 60, 100. So this is log, and this is 10 to the third. No, 10 to the second, 2 zeros. This is 10 to the 1. Sorry. Anyway, 100, 200, 300, up to 1,000. So if I want to plot on this paper, let's say I'm going to pick something in the middle right here, point number 6. It is here, point number 6. And this is 10, 20, and then this is 100, 216 approximately right there. So that's how you can plot it. And now you can see that you could see this curve. But you can imagine that if I went 1, 2, 3, 4, 5, 6, 7, 8, all the way to 1,000, my paper would be huge, right? So this is a way of plotting a curve on a manageable piece of paper. Questions about this? Does it make sense? Does somebody want to tell me what I just said? No. Daniel's going, not me. Want me to do it again? Sure, Daniel. Okay. All righty. Okay. So let's first think about this. Remember, we said logs, right? I think I should erase this. Okay, so we said logs, right? So essentially what this is doing, remember up here, I talked about the logs, this exponent number right here, meaning the number of zeros. That one. So this is 10 to the third, right? Because it has 3 zeros. This is 10 to the 2. 10 times 10 is 100. 10 times 10, times is 1,000. And this is 1, 10. This is 10 to the 1. In other words, there is no exponent, right? So that's 10. So this is the representation of this, right? I can see you, John. Yes. Yeah. Okay. Ben, yeah. If you say so, lady, right? Okay. So in order to keep it's this on a single piece of paper, what we've done is we have collapsed these. So when I read this is 1 2 3 4 5 6 7 8 9 10. 10, here's 10. And the second major breaking is 20 30 40 100. And the third major breaking is 2 300 to 1,000. So if I plot these, this is X and this is Y, right? So the X-axis, the first one is 1 to 1, 1 on 1. So that's this first dot right here. The second dot is up 2 and 8. Oh, yeah. Oh, excuse me. 2 and 8. So these count 1, 2, 3, 4, 5, 6, 7, 8. I'm not any brighter than the rest of you, right? And the third one is 3 and 27. So this is 3. That's 10. This is 20. And this little bit right here is 7. Good enough? Yeah. You won't ever be asked to plot anything like this, but you should know what semi-log paper is and sort of how it works. I'm sure you won't see it on the exam, right?
Hey, Jill, do you have a second?
Yes, of course.
Sorry, so point 0.7 at 343. I'm looking at that on the graph and it looks like it's, unless I've just got this wrong, it looks like it's at 400 and not at 343. So that's why I was quiet because I was like a little confused there.
Okay, so we have 0.7, right?
Yeah.
And so this is 10, this is 100, 100. And then we have this is 200, and this is 300. Yes, you're right. That says 400. So they plotted it wrong. It should be more like here.
Okay. All right. So that made me think that I just wasn't. All right.
No,
Thank you.
right. Yeah. Because 10, 20, 30, 40, in here. So yeah, you're right. This one looks a little bit high, like 43. So if this is 1, 2, 3, 4, 43, 400, 343. Right. It should be here because this would be 400. You're right.
All right.
Oh, they made a mistake. Oh, well, I'm just glad to see that you are paying attention.
Yeah, I'm awake. I promise.
Yeah, that's good. This stuff will put you right to sleep, right? So, yeah. So, why do we care about logs? Other than the fact we can plot the curve on a single piece of paper. So, why we care about logs is that we use a logarithmic death rate. So every time there's a 1 log reduction, there's a 90% reduction in the number of microbes present. So let's say you start out with 100,000. Notice that there's 3 6 zeros here. And then you have a 1 log reduction. So we lop off one of the zeros. And now we have 90% of the population. Then we lop off another and we have we have a reduction of 99%. And then we lop off another one and we have 99.9 and et cetera, 99.999. Essentially, you could never get to zero, but obviously you do, right? But mathematically, 90% of 90% of 90%. But what we can see is that each time interval is designed to destroy 1 log or 90% of the microbial population. At
What's the maximum? How many logs
uh,
total?
so retorting is 12D. 12.
Okay, so that it okay. So that's the maximum. Okay.
That's why it's set that way mathematically. So retorting is 12D process.
Perfect.
Pasteurization is less, right? Less heat.
Okay.
Yeah. So good question. Good question. So at a constant temperature, the same percentage of bacterial population will be destroyed in each time interval. So each time interval. So we can calculate how much time it's going to be to destroy 90%, and then the same amount of time for the next 90% and the next 90% and the next 90%. How do we figure this out? It's a combination of experimentation and calculation. And it's done by a process authority, which I didn't realize. A process authority is not like a building or a company or anything. It's a person, right? The process authority is a person. And that person works with you to, based on your experimentation and all that his experience at calculations, how it's done. So the process authority is a person who's been to school and who has been certified as a process authority. When I first thought it, I thought a process sounds like a company or something. Anyway. So that's how you figure it out. So you do, some experimentation and then you do that. The math. Okay. So the thermal death time, right? Time, D value is time. It's in minutes at a given temperature for 1 log so the D value is your time in minutes for 1 log reduction or a 90% reduction. So an example I have here is at 250 degrees, which is a retort, right? A pressure cooker. So 250 degrees, it takes 4 to 5 minutes to kill 90% of the population of the flat sour thermal feel. And it's harder to kill the spoilage organism, which is a spoilage organism. It's harder to kill the spoilage organisms than it is the pathogens. So if you can wipe out the spoilage ones, you know you've done a good job on the pathogens, right? So 1D for this for flat sour spoilage is 250 degrees, a constant 250 degrees for 4 to 5 minutes. And that'll give you a 1 log reduction. And that's called the D value. So if flat sour, which is the Bacillus stereothermophilus, or something along those lines, takes 4 to 5 minutes. Clostridium botulism only takes 0.21 minutes. So like I said, at 250 degrees, if you can kill off the flat sour, the bot is gone, right? It's gone. So as you increase the temperature, now we can't go over 250. So, but if you increase the temperature, the higher the temperature, the shorter the time, right? So low acid canned foods are processed to 12D, which is less than 1 spore per 100 million cans. So in order, if this is 1D up here, 4 to 5 minutes, a 12D process is going to be 48 to 60 minutes, or 12 times 4. Right? Sure, lady. Whatever. Questions? None? I have flummoxed you for sure, right? Okay, that's the D value. So when you think about D value, you're going to think about time.
Jill, I have a question.
Yes, please.
Does the time and temperature, well, the temperature I'm sure stays the same, but does the time change if it's more acidic or lower pH?
Yes. So there's all kinds of things that can affect the time. One is how liquid it is, right? Versus
Yep.
whether it's solid, versus dog food versus chicken noodle soup, right? So chicken noodle soup, because there's convection inside the can, going to get a shorter period of time. While dog food, it's a solid, so it's done by conduction, which is a lot slower. So then the pH of the food is going to make a difference. The more acidic it is, the easier it is to kill off the pathogens, right? So that's going to make a difference. Those are the major ones I can think of right now. So the thermal properties of it, the size of the can,
Right.
bigger can, right? Takes longer for the heat to get to the center or to the cold point in the can. So a bigger can is going to make a difference also.
Okay. Thank you.
Yeah, that's a very good question, John. Right. So all of those things come into play. So what happens if I want to change the temperature? Let's say I want to make it hotter or colder. So the Z value is the temperature. So this one is temperature. The Z value is temperature. So as the temperature goes up, the time goes down. As the temperature goes down, the time goes up, right? The hotter it is, the quicker you can kill them off. The cool, as you choose a different temperature, the lower it is, the longer your time's going to be. So let's think about cook chill versus sous vide, right? That's the best way to think about it, right? Cook chill, you bring it up to a nice warm, 180, 200 degrees, bubble, 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 bubble. So you have a short period of time for pasteurization. Sous vide, because the temperature is low, it could take you hours to pasteurize. Does that make sense? So think about it that way, right? So an organism's Z value is 18 degrees. So this is how you calculate that. So if we have the Z value of 18 degrees Fahrenheit, our cook time it's going to be 232 for 3 minutes. But if we raise the temperature to 250 degrees, then it's going to be 0.3 minutes. So in other words, there's going to be a reduction in time. And both of these are equivalent processes, right? So they're equivalent process. You're going to get the same log reduction in microorganism, whether you use a longer, lower cook time or a shorter, faster cook time. I don't think knowing how to do the math is so important, but so here we see our logs right here. 1, 2, 3, 4, 5. This is semi-log paper, just like I was doing at the beginning, right? So the logs are going up the top and the heating time is going across the top, the bottom. So the D value is here. It's the temperature and the number of survivors, right? Here, shrinking. And this is the same, this is a different one. This is your D values or minutes going up and your temperature going across. So, if you like graphs. So I think it's kind of hard to keep these two separate. So I kind of came up with this. Time, temperature, D comes before Z in the alphabet. Time comes before temperature, so D comes before Z in the alphabet. Now, if you come up with something better than that, let me know, right? So but essentially the D value gives you amount of time, and the Z value gives you the temperature. So the F value is like a summation of the whole process. I don't know why they came up with F. I don't know. And F sub 0 assumes a 12D reduction. So that's what the F sub 0. But because otherwise it would be written F and then the temperature, 250 degrees, and 48 minutes for a 12D, which is, so F is like a summary of your process. Questions? So while I've been talking about retorting, which is 250 degrees or pressure for low acid foods, the same types of calculations are used for pasteurization, whether it be a sous vide process or a milk process or whatever it is. The same calculations, the same type of calculations are used for all of those, only depending on how severe it is and what the microorganism is that you're trying to kill. Anybody? Any questions? Was that helpful? Yes. The only person I can see is Ben, and he's shaking his head yes. So, yeah, Ben. Thank you. Okay. So I just put this in here to remind you that, when that how to count minus numbers, right? Right. So just remembering that the curve, right? Counting them this way and that way. So just remembering that. So this is a summary of the terms. I won't go through that again. Once is enough. Once is enough. So adding to this, when they actually calculate your process, they can include, and they do include the come up time. So how long does it take your retort to get to 250 degrees? And then how long do you take to cool it down? And so there are microbes that are being destroyed in these areas right here. So what they do is they calculate that in to shorten your cook time, because obviously you want to shorten as much of the cook time as possible so that you don't destroy the food. Okay. And I want to give a shout out to Jeffrey Kuzminer, the RCA, because he was the one that helped me with learning all of this stuff. So he's the guy, in case you recognize that move, he's the editor for the culinology text, in case you recognize his name. So we talked about can size, conduction, convection. I answered, I think, John's question about that. So what it's all about, bringing the cold spot inside the can to the correct cook temperature. And if it's convection, it's going to happen a lot faster. And usually this cold spot is more like down here, especially in a solid food. It's closer to it's not exactly in the middle, it's closer to the bottom. All right, any questions? So pasteurization is the thermal treatment that's used for refrigerated shelf stable or refrigerated food. Destroys pathogenic microorganisms. And then we talked about when you talk about milk. So when we talk about pasteurization and we talk about milk, right? So that pasteurization is the old way we used to do it. It's like a big pot and you cook it for 30 minutes. Notice the temperature is 143 degrees because you can't cook milk higher than that. And the time is 30 minutes. But then they came up with a heat, they call those things, the heat pipe, where you have all those pipes. So high temperature, short time. Notice that when we went from 143 to 161, we reduced the time to 17 seconds. So high temperature, short time. So this is the milk we see in the refrigerator, in the supermarket today, usually high temperature, short time. We can also do ultra pasteurization, which is a higher temperature, 280 for 2 seconds. Notice how the temperature is rising and the time is going down significantly. And this ultra pasteurization is the shelf stable milk that's on the shelf, right? The box milk that's on the shelf. And the way they know whether milk has been fully pasteurized is they check for an enzyme, alkaline phosphatase. And if that's been destroyed, then the milk is properly pasteurized. So milk is a low acid food with a pH greater than 4.6 and a water activity greater than 0.85. So it's considered a potentially hazardous food. So then we talked a little bit about cook chill. So generally, I believe everybody's process is different. I believe you have to have a process authority to figure this out, but cooking to at least 180 degrees. I think Jenny told me that because they do a lot of cook chill at Village Green Foods. That was their original. That's where they started with cook chill, and was 180 degrees. She bags at 180 degrees, so she cooks it higher than that. And she says when she does that, then they don't have any problems with the food. It'll last. If you do cook chill, you have to have a HACCP plan, even if it's in a restaurant. Essentially, it's an anaerobic environment. So the good things about being an anaerobic environment, it prevents or slows the growth of aerobic spoilage organisms, such as Pseudomonas, which is Pseudomos yeast and molds, and slows oxidative rancidity. The risk of an anaerobic environment is outgrowth of BOT and listeria. Well, that was a lot of information in 50 minutes, right? So, anybody have anything you want me to go over again? If I were to go over it again, if I were to summarize the most important thing, I don't want to do that. If I were to summarize the most important things, so let's do that. In summary, let's go down here. In summary, right? It's a time, which is D value, temperature, which is Z value, relationship. This is why I don't type. Oops, hi there. Okay, so in summary, it's a time-temperature relationship. And the F value is a summary of your process. Right? God, I'm showing my ignorance. Okay. And 1 log reduction is 90% of the microbe. If that's all you know about this, you're probably better off than you were before, right? Did I leave anything out? So it took me 50 minutes to tell you 3 lines worth of information.
You were really thorough about it, Jill.
I was. Well, it sounds so hard, right? And, if we kind of gloss over the mathy parts, right? And just all we need to do is understand it conceptually. We don't have to reproduce it. We only have to understand it conceptually, right?
Yeah, I'll probably have to rewatch the log reduction portion because my kids had a popcorn catastrophe, so I had it in one ear while Honey, I Shrunk the Kids was going on, and the kids were freaking out about popcorn. So
No.
we'll see. We'll see if I rewatch that one.
That's all right. It's there for you to watch as many times as you want, right?
Perfect. Perfect.
Okay, well, that's great.